So we've made real predictions that have been verified, that demonstrate that we have actually understood what's going on for basically the right reasons.
What's up, you scholars of enlightenment? I hope you've had an incredibly fun and relaxing weekend. Simulating the global climate is incredibly complex, potentially involving huge numbers of variables that describe and relate nature's chemical, physical, and biological processes. This complexity has led to public confusion about the validity of climate prediction. In an observational science such as the study of the climate, or cosmology, or evolution, we don't get to do controlled laboratory experiments. We only have one test subject, the planet Earth. And we are only able to run one uncontrolled experiment at a time. It would be unfortunate indeed if this experiment had to run its course before we could say anything about the likely results. However, many still seem to think that modelling and predicting the climate is simply too difficult, akin to gambling in Vegas or playing the stock market, and that climate models are not particularly trustworthy when we're looking to inform public policy. This seemed to be the tack taken by Canadian psychologist Jordan Peterson during his recent interview on the Joe Rogan podcast. Following that appearance, I wanted to understand and explore the limitations of climate modelling and dispel some of the myths around what climate models are and are not good for. To help me do that, I chatted to NASA's Gavin Schmidt. Gavin is a climate modeller at NASA's Goddard Institute for Space Studies, where he uses coupled ocean-atmosphere climate models to investigate the interactions between large-scale climate systems, such as the ocean and wind currents, to understand natural variability and how climate responds to human-made forcings. He also works to reconcile paleoclimate data from ice cores, tree rings, and other proxies with modern-day climate models. He was until recently the senior climate advisor at NASA. So, Gavin, first up, modelling the climate of the entire planet seems like an incredibly difficult task. So, how do we go about making this modelling tractable and even possible? Because a common refrain I hear amongst people who are more climate change skeptic, or at least climate modelling skeptic, is that this is just something that's too hard for us to do. There's too many variables. We heard Jordan Peterson on Joe Rogan sort of flirting with this idea that climate is everything, but the models don't include everything. How do we make this more tractable so that we can make some headway?
Well, it's in the same way that we do this in any scientific endeavor, right? You try and limit it to the things that you think of as important. And then as you progress, you add more things. And so people think that we just started climate modeling yesterday. No. We've been doing this for 40 years. And at the beginning, people focused on one or two aspects. And so Suki Manabe, who just won the Nobel Prize for physics, they started off in the 1960s thinking about radiation. So the solar radiation coming in, getting absorbed by ozone and by water vapor, getting to the surface warming up, the infrared radiation coming up and being absorbed by greenhouse gases and by clouds and in the stratosphere and by water vapor and all the rest of it. And that, it turns out, was extremely powerful. And so the reductionism that we see in all sorts of scientific endeavors has been super powerful when it comes to climate. And so 40 years ago, there were folks working on the radiation part. There were other people working on the dynamics, like the fluid dynamics, the weather systems moving around. There were other people working on the sea ice or the carbon cycle. And as time has gone on, what's happened is it's a little bit like the Borg. Climate has come to encapsulate all of those things. And so the first climate models put together the radiation parts with convection and then the dynamics in relatively simple ways. And it turns out that they were very skillful. They were able to tell us things about the system, despite the fact that the system was much more complicated than that. And so this has been very much a process of normal science in the Thomas Kuhn sense, right? So little bits, adding in, and every time we make things a little bit better, right? And so after 40 years of this, and with the massive explosion of computational capacity, the climate models have come to incorporate, a lot more of the Earth system, from ice sheets and sea ice to the carbon cycle to atmospheric composition, aerosols, the ozone layer, the deep ocean, the soils, the biosphere, the mountain glaciers. All of these things are now incorporated. And as we've expanded the scope of those models, they have become more skillful, right? By putting more in, they become more realistic. And we end up with models that are able now not only to explain what we see in the weather or in the climate or in the changes over the last 100 years, but they're able to project things going forward in a skillful way. And we've been able to test that.
Is it fair to say that we look more on a broad scale with climate? So there's a misconception where people think we can't predict if it's going to rain, in 3 years in China or whatever it might be. Right. But when we look at more broad scale patterns, it's easier to understand things on a wider scale over a longer period of time than it is to look at the minutiae of a very short period and very localized. Is that a fair assessment, or is that
kind of, but not quite? I mean, so okay. The question is where does predictability come from, right? So what are the physics that allow us to make predictions, right? Because we're not making predictions about human behavior, right? That's impossible. We're not making predictions about technology, also impossible. Yeah. We're making predictions about physical quantities, and so where in the physics is there predictability? And so that's been the quest over this whole period. So where is there predictability? Now, in weather systems, there's predictability because I can track. If here's a storm and there's the circulation, I know that the storm is going to be moved by the circulation. It's going to be stretched, and so and there's predictability because I can follow that individual storm system, and that's the basis of weather forecasts. That's the basis of the success that they've had, for 4, 5, 10 days forecasts. Okay, but we don't need to track individual storms for 40 years. They don't last that long, right? So there's no predictability when it comes to individual storms on that kind of timescale. Yeah. But it turns out that there is predictability from the boundary conditions around climate, right? So if I change the surface, if I chop down a whole bunch of forests, then that changes the climate in a kind of permanent and systematic way. If I change the composition of the atmosphere by adding carbon dioxide or by depleting ozone or by adding volcanic aerosols, then it changes the climate in a predictable way. If the sun becomes brighter or more active or less active, that changes the climate in a predictable way. If the orbit of the Earth changes on 10,000 year timescales, 20,000, 40,000 year timescales on longer, that changes the climate in a predictable way. And we know that it does because we know that the seasons are predictable, right? We know that winter is colder than summer in the Northern Hemisphere, right? And why is that? It's because of the tilt of the Earth and the large scale change in how much solar radiation is coming to any particular part of the climate, right? So we know that the climate responds to those boundary conditions. And it turns out that if we can predict those boundary conditions going forward, we have predictability of the climate system. And so we can say with confidence that increasing greenhouse gases will increase the surface temperature. We can say that if the sun became brighter, it would increase the surface temperature and the stratospheric temperature. We can say that, when there's an ENSO event, an El Nino in the tropical Pacific, that will change the climate in a predictable way. If you have a lot more El Ninos or a lot more La Ninas, again, these things have predictable and verifiable impacts. When a big volcano goes off, right, we can predict that the amount of stuff that it puts into the stratosphere will cool the climate for 1, 2, 3, 4 years, perhaps, depending on how big it is.
So physics and these models can give us sort of higher level, predictable ideas about what will happen with the climate, and we don't necessarily need to know exactly what's going to happen in the weather in 25 years or whatever it might be. We can get these cliff note ideas out from the physics and the modeling.
Yeah, I mean, so we can't predict the weather beyond 10 days or so, right? So we all understand that, but we can predict the statistics of weather over much longer periods, because they respond to those boundary conditions that set the tone of the whole climate, right? We can say things about the intensity of rainfall. We can say things about the frequency of heat waves, the intensity of storms, where storm tracks are changing. I mean,
it's the signal rather than the noise, isn't it? We can see a signal even if we can't look at the exact noise of the system. Is that would that be a fair representation?
Right. I mean, I'm sure you know this. Like, some person's signal is another person's noise, right? So when you're predicting the weather, the climate change part is irrelevant, and you can just go from what you see and make predictions. And for the climate, then the weather, the specific evolution of a particular weather system, that is the noise for the climate system. But obviously it's not noise in a to be neglected way. I mean, obviously it makes a huge difference, but we can say something about the quality of that noise, right? We can say something about the frequency of that noise. We can say something about the magnitude of that noise, and where it's big and where it's small. And so we can say things about the statistics of weather, even 30 years ahead, 40 years ahead, 100 years ahead, even if we can't predict exactly whether there'll be a storm in London on July 4th, 2082.
That's a really nice way of putting it. What would you say are some of the most important, or as you say, skillful climate predictions that we can make, and sort of the more simple science behind them? You mentioned more CO2 leads to warming. Warming is going to lead to melting ice. These seem relatively settled science, relatively, extremely important things that we have a good handle on why they're happening and that they will happen.
Right. So why things are happening is a fundamental question, and your question really kind of leads into, well, how do we know why things are changing, right? Yes. So we know that the planet has warmed, right? So we know that it's warmed more than a degree C over the last 100 odd years. Most of that warming has come in the last 60 years, and there are lots of different things that can cause the climate to change, right? I mean, so, you look over 4 billion years of Earth's history, and we've had the wobbles of the Earth's orbit, the sun, the outgassing from massive volcanoes, plate tectonics changing the continents around, asteroids coming out of nowhere and destroying everything. There's been many, many, many different things that have caused the climate to change, right? So you don't just see a climate change and you say, oh, well, I know what caused it, without doing any tests, right? So you have to test that. So when we look over the last 100 years, we can calculate the consequences of any of the different plausible hypotheses that we have. And it turns out that they all have different fingerprints. They all have different patterns of change in the system that we can then go and look for, right? So we're looking at this a little bit like a crime scene investigation. We can't rerun the past, but we can say, well, if it was the sun that did it, isn't it the sun what did it? Isn't that
It's the ultimate who done it, isn't it? It's the
yes.
Yeah.
Then you would expect certain things, right? You would expect that the surface would warm, sure, but you'd also expect the whole atmosphere to warm because you're having more radiation coming in. That's an interesting pattern, and it turns out to be very different from the pattern that you get when you increase carbon dioxide. And it turns out that carbon dioxide, which is something that has been known since the 1960s, causes the surface to warm, but anything above the tropopause, everything above in the stratosphere and the mesosphere, it causes it to cool because carbon dioxide is more efficient in those areas at emitting than it is absorbing because of the way that the spectral absorption works. And so what you have is a very different pattern for carbon dioxide driven change than you do for solar-driven change.
Because this is a common refrain we hear, isn't it? I even from discussing this very naively, I'm not an expert in the field. As soon as you bring this up, people go, "Oh well, it's probably just the sun or it's something else." But this has obviously been considered in the field that it could be these other things and ruled out.
Yes, and it has been ruled out. Plus, the changes in solar radiation, it kind of peaked in the 1950s and has been slightly decreasing ever since. But it's not a very big effect. Anyway, and even if we got it wrong by like an order of magnitude, it would still have the wrong pattern of change in time and in space, right? People say, oh well, maybe it's the ocean. Maybe the ocean is just like putting lots more heat into the atmosphere. Well, if the ocean was putting lots more heat into the atmosphere, the ocean would be cooling. But we don't see that. We see that the ocean is warming. Yeah. The ocean warming tells us that something is changing at the top of the atmosphere because of conservation of energy. Conservation of energy is a very powerful trick that we have in the physics arsenal. So if energy is coming in to the system, then there has to be more coming in at the top. What changes the radiation balance at the top? Things like greenhouse gases or the sun or aerosols. And we look at each of those things and we say, okay, well, have we decreased the amount of aerosols in the atmosphere? The answer is no, we've increased the amount of aerosols. So it's not that. Have we increased the amount of greenhouse gases? Do we expect that to cause more energy to come in than is leaving? Yes, we do. And so where is that energy going? It's going into the ocean. And when people back in the 80s and 90s kind of set up tests, they said, well, if you're right about this whole greenhouse warming, anthropogenic change thing, then, we'd be expecting to see the change in the ocean. And at the time, people didn't have the data to say whether the oceans were changing. And so it was a real prediction that if we were right, that things were warming up because of the increase in carbon dioxide and the other greenhouse gases, then we would see warming in the ocean. And the folks that said, "Oh no, well the ocean, climate sensitivity is zero," then you would see no change in the ocean because the surface would respond super fast, and there'd be no lag because of the heating of the ocean. So, and none of those things were true, right? So when we got the data for the heating of the ocean, what we saw was the heating of the ocean exactly at the level and at the rate that we expected because of the increases in greenhouse gases. So we've made real predictions that have been verified that demonstrate that we have actually understood what's going on for basically the right reasons.
And that's the important thing, isn't it? Like you said, with any model, it has to be skillful. It has to make predictions, and then the data that we get has to fit those predictions. Why? This is again a very naive question, but I still think a lot of people don't understand it. Why are these small changes? You talked about 1 degree, 2 degrees. People talk about 3 degrees as sort of a hellish increase over the next 100 years. Why are these such a big deal for the planet and for society when it's something that we barely notice on a day-to-day basis? A lot of people say, a couple of degrees warming, don't really care. Why are these models telling us that this is such a bad thing if we get to 3 degrees, 4 degrees of warming over the next 100 years?
Right. I mean, excellent question, and one that we get a lot. And it turns out that the scale of temperature change for a planet, where you have a lot of counterbalancing things, it's actually pretty limited, right? So you go back to the last ice age, right? And that was about 20,000 years ago, the peak of the last ice age. You had glaciers all over the UK, the Fenno-Scandinavian ice sheet coming all the way down. In North America, you had the Laurentide ice sheet all the way down to New York. Massive amounts of water removed from the ocean and put into ice. The sea level was about 120 meters lower. Wow. Tundra, mammoths, cavemen. Massively different planets. But the temperature change between kind of the pre-industrial and then is only about 6 degrees Celsius, right? So that huge change in the global mean temperature was only about 6 degrees. And so now we're talking, we've seen like 1 degree. Okay, we're seeing a little bit more than that. It's about a fifth of the ice age change, right? But in the other direction. Yeah. And then when we go forward and you say, okay, 2 degrees, well, 3 degrees, 4 degrees. Well, now you're talking about almost as warm again as the ice age was cold. Yeah. And so for the planet, that makes a difference. And we can see that a difference that even 1 degree has made. We're seeing the changes in the mountain glaciers. They're disappearing all over the world. We're seeing the change in the sea level, which is rising, pretty much continuously. We're seeing the change in the statistics of weather. So we're already seeing that 1 degree in the planetary scale makes a real difference to local phenomena, local ecosystems, local climate conditions, and even in the weather.
Yeah, makes sense. So any predictions that obviously come out of climate models, they come with associated uncertainties. And I think there's a lot of stuff around this that people don't understand as well. How are these uncertainties estimated? Because obviously we don't have multiple Earths that we can play with and go into the laboratory and mess around with. So how do we get a handle on those uncertainties so that we can we can say how powerful our models are and how skillful our models are?
Right. Okay. So there's basically 3 different kinds of uncertainty. Right. So there's the uncertainty associated with what the actual world will do. Yeah. Right. So we don't know, will people reduce carbon dioxide emissions? Will they burn all the coal? Will they discover a new technology? Will they do? We don't really know. Like, how will economics, will there be a war? Will there be a this? Will there be another pandemic? Like, none of these things are predictable by climate models or indeed, pretty much anybody. Yeah. And so there's that kind of scenario uncertainty. What are we going to do? Are we going to cap carbon dioxide and other greenhouse gases?
Is fusion going to come online and everything goes away?
Yes, when will that happen? Yeah. Like, traditionally it's 30 years, but we'll see.
It's been 30 years for the last 30 years though. So
well, it's been, yes, well indeed. Or are we going to burn all the hydrocarbons that we can? And obviously there's some people that want to do that, right? So are they going to win, or are the environmentalists going to win? Yeah. That's not a probabilistic calculation.
But we can model under certain scenarios, I guess, business as usual.
But we can do, okay, well, so let's just assume that we get it under control, or let's assume that we don't get it under control, and that kind of bounds the space in which we have to work. And so the numbers that people talk about, the 1.5 to 4 degrees thing, that's basically the space that we have control over. Yeah. Now, there are other uncertainties, right? There are uncertainties in the fact that the models are not complete. The models have to make approximations, and different models make different approximations. And so there's a structural uncertainty in the model. So if you take one model and it says, well, if you increase carbon dioxide, it's going to increase by, yay degrees. And then another model says, well, yay +2, right? And you go, okay, well, that's uncertainty in our understanding of the system. And that's the bit that we can really focus on as physicists, is like, how can we drill that? How can we push that down? Yeah. And we do that by looking at out of sample tests. We do that by looking at paleoclimate. We do that by upgrading our comparisons to the processes that are going on right now. We throw up new satellites that tell us something new about rainfall or convection or clouds, and we use that information to kind of narrow the possibilities for these models as best we can. And that's a process. So there's that structural uncertainty, but it turns out that structural uncertainty is much smaller than the scenario uncertainty. And then you've got the uncertainty just because of the noise, right? That you mentioned before, the chaos of the weather and the chaos of things like El Nino and ocean eddies and all of those things. And that's pretty much irreducible, right? So we can't predict that more than a few days ahead of time. Even El Ninos, we can't really predict them more than 6 months to maybe a year going forward. And so, the ability to say what El Nino is going to do or what the weather is going to do in 2050 is zero. And so there's an irreducible amount of noise that's associated with the weather. But again, that turns out to be small compared to the structural uncertainty. So the different models doing slightly different things. And all of those are small compared to the uncertainty in what the trajectory is actually going to be because of our actions.
So in terms of those structural uncertainties that you talked about, did you say I think when we chatted offline, there's about 30 groups now running different models, aren't they? And we put those together. I guess, thinking I'm a particle physicist, there's a potential there for some sort of systematic errors where people are doing similar things or using the same styles of computing. How do we drive down those errors?
So that's a very real question. We all have pretty much the same access to computational infrastructure, and that means that we can't really, everybody is kind of limited by that. So we're pushing the envelope, but the envelope is the same for everybody. And so there are some things that we can't include that is the same for everybody. And so that's a systematic difference. A systematic commonality in the models, a common assumption that could lead us astray. There's no question. So you can't just take the models as is, right? You can't just say, "Oh, here are a bunch of models, then let's average them, and that will be the truth," right? No, that doesn't work. It's a reasonable heuristic for most things, but it doesn't tell you that that's the case. So you have to test them, right? You have to test them in out of sample conditions. And so I mentioned the last ice age earlier. The last ice age is a great example of a big, massive global shift because of changes in greenhouse gases, because of changes in the orbit, because of these massive glaciers. We can test that. We can say, okay, well, if you give the models the situation like the LGM, do you get temperatures that are like the temperatures that you got then? And we can do that. And sometimes models fail. Right? Sometimes models fail that test. And then you can say, okay, well, they're either not sensitive enough or they're too sensitive. And we can we're just going to use the models that do well on that test. Right. And so that allows us to narrow the range by winnowing out models that fail, big, large scale tests.
And I think this is a lot of work that people don't see, right? They don't see, oh, that failed, so we're going to do something else. We're going to upgrade the model. That was a good idea, but it didn't work properly. I think people don't see this, and therefore they're more skeptical than they might necessarily need to be.
Yes, I mean, in the public discourse, these models kind of come deus ex machina, and nobody sees how they're developed or why they're developed or how they're checked or absolutely. And so people say, oh, well, here we know what's going to happen in the future, and but how do you know? And for folks like Peterson, who've not really given this any thought whatsoever, it's like, well, how do you go about changing their looking at different variables? And it's like, well, that's what we do. We look at different variables and see which ones give us more explanatory power.
It's like when I hear people say, "Oh, couldn't it be the sun?" I just think a serious person in that field is going to be like one of the first variables that comes up in the discussion at the first coffee meeting over what goes into the model. This is not some that thing up there, that really hot thing that.
And surprise, it was one of the first things they tested, right? You go back to that Suki Manabe paper in 1967. What happens when you change the sun? What happens when you change carbon dioxide? What happens when you change water vapor? Right? The fundamental variables we've known about for 40 years, 50 years. It's you know what? I mean, you can read people talking about climate in in the kind of late 19th century, James Kroll, like talking about the heat being transported by the currents in the North Atlantic, talking about the changes because of orbital wobbles in the Earth's orbit. People knew a lot, even 100 years ago, and we know more now, and we know much more quantitatively, because we have satellites that are measuring, the specific processes that we care about. We have 100 more years of quality data than they had. If you look at some of the data sets that they were trying to match up to in the 19th century, it's really grasping at straws, but doing really well despite that. We have much more data now. We have many more cases, field experiments, natural experiments like the eruption of Pinatubo that allowed us at that time to make real-time predictions for how the climate would change over the next few years that panned out.
Is it possible that we're missing some key variables which could be very important in the prediction of climate? I guess it's always possible that there could be. People talk to this. People use an example, and I know you've used this example before, of the consensus of chemistry models on stratospheric ozone levels in the 1980s, and there simply wasn't a particular piece of chemistry involved in those, so all of the models missed it. Is it possible that we're still missing some key variables?
Yeah, so what happened there was that the chemistry models didn't include what's called heterogeneous chemistry on surfaces, because they didn't think that was going to be a big deal, because there aren't that many surfaces in the stratosphere where the ozone was being depleted. But it turns out that if it gets cold enough, in the Antarctic area, you get what they call these polar stratospheric clouds that suddenly allow for a lot more chemistry to happen, that depleted the ozone even more, that made it colder, that produced more of these particles. And so you ended up with this massive shift that produces the ozone hole that came as a total surprise to everybody when it was first noticed in 83 and 84. So are there things that we could be pushing the climate towards that we haven't seen now, but that will only get triggered when we pass some threshold?
Yeah.
So the answer is yes. We try and look at warm climates in the past, like the Pliocene, about 3 million years ago, about 3 degrees warmer than today. Can we explain everything that we see there? Pretty much, but maybe there's some stuff there that needs to be done. Like the Eocene, the Cretaceous, much warmer climates. No sea ice in the Arctic to speak of, despite the fact that you had a polar night. How do you keep the poles warm when there's no sun? Right, and keep them warm for millions of years. Not just for a little bit. So there has to be some fundamental thing that's going on there. Can we match that? We're doing well, but are there still potential missing things that happen in very warm climates? Yeah, it's possible. But it may be, if we avoid those very warm climates, we may never know.
Yeah.
Right. So, which would be a good thing. Or we can go there and you say, oh yeah, you know what, we missed out that really important thing. And it's like, oh yeah, no, bad us. But like now it's too late, right? So yes, there are irreducible unknown unknowns as you push the system further and further from the point where you have all of your good data, which is now. And so that's a real concern, but I don't know that it's any comfort to anybody to know that there are unknown unknowns that could be triggered at some point.
Makes sense. What would you say are you talked about the better data that we can get nowadays? Obviously we have things like satellites, ability to do a lot more computational processing as well. What would you say are some of the biggest areas where we need to get more data to improve these models? I know when I was at CERN, the cloud experiment was just coming online to deal with, muons and aerosol formation when muons come through and such, and similar things. Is that still an area where we need more details about what's going on? What where are the problems in our understanding of the physics and the chemistry at the base level that could be improved?
So that's a very interesting experiment that you bring up. So the initial impetus for that experiment was the idea that cosmic rays would be coming in and they would change aerosol formation processes that, as over a solar cycle you get these changes in the cosmic radiation, that would be an important factor for climate.
And I remember there was a chap, was he called Skarsgård or something, who seemed to think that the whole of climate change was due to cosmic rays and us going through the arms of the galaxy and all these sort of odd things that people push back against.
I also forget his name instantly, but I know exactly who you're talking about. So that was a theory, and that was tested. But what they did, and this is all credit to CERN, that it took like 4 different iterations, I think, for the proposal to be accepted, and it morphed from being let's test this slightly crazy idea to let's look at the processes involved in aerosol formation. Right. Let's build the biggest aerosol chamber that we have that uses the ionization from CERN to spark things off. But what we're going to do is we're going to instrument that so that we can tell exactly what particles are being formed, what is the chemistry involved, and change everything. And what they did was brilliant. And they ended up with a really fundamental set of measurements that really tell us how amines and sulfur dioxide and sulfates all kind of mingle together to produce particles. And we're still embedding that information in the processes that we include in the climate model. So that turned out to be very, very useful, even though it kind of it was a negative result for the folks that started it off. But
you'd be surprised how many experiments at Stern start with a crazy idea and then go on to be something else. That's a very common thread by the.
That'd be an interesting thing to chat about. Maybe another time.
Yeah, another time.
But one of the things that we don't know is so we're kind of drilling down on the processes of aerosol formation and clouds. But we don't still know how many aerosols there are in the atmosphere, what kind of aerosols, what kind of mixing state are they in? And it's been a hard thing for us to measure from space. So we have ground measurements, but they're only in small places, and so they don't get the full picture. So we've been wanting to have global pictures of where is their dust, where is their sea salt, where is their sulfate, and we needed to have a polar orbiting satellite that measured those kinds of things. And it turns out that you can't measure it very easily just in the visible or just in the infrared. You need to look at things like polarimetry because the different shapes of the different particles polarize light in different ways. And so the fingerprints of what's in the air can only be seen with a kind of special kind of instrument. And we've failed to have a sustained campaign of that kind of instrument in space. Now, that's been a bit of bad luck. We were involved in a mission that would have done that, but it didn't achieve orbit. So that kind of sucks. There was a French mission that was there, but it only lasted 9 months. But we have 2 new projects in the works that are going to do a much better job. There's the PACE mission, which will launch, I think, in 23 or maybe 24. And then there's these new, what's called the Earth System Observatory that NASA is putting together that will have, multiple satellites with multiple polarimeters to get a really good sense of what's going on. And so that will really help us narrow down the uncertainty in atmospheric composition.
Sounds really good going forward. So I've just got 2 more questions, and I want to kind of move towards more of a sort of societal impact of these models. So what would you say, for someone who's skeptical about these models and how useful they are, what would you say is the most important thing that they've been able to predict, both into the past and going forward, that could convince someone that these models are skillful, accurate for the most part? What would you point to as the predictions that they've made that we now see coming true? Because you see a lot of people saying naively, oh, these models have all failed, they made this prediction and we don't see it now, and then people tend to sort of run off and really sort of be incredibly skeptical of these models. What would you point them to say these models are skillful?
Right. So, first of all, there's a lot of people that make predictions that they say are based on models, but really aren't. They're just basically just what they came up with. And so, it's pretty easy to go back and find people predicting all sorts of stupid things that were stupid at the time that they said them. And then now it's like, oh, see, you didn't. So you have to really focus on what the models actually predicted, right? And so, and we do that. We wrote a paper a couple of years ago that said, okay, let's take those old models. Let's take those models from the 1970s and the 1980s and the 1990s and see how well they did. Yeah. And it turns out that they did really well. They did really well for things like temperature. They do really well for things like, what happens with a big volcano. They do well when it comes to sea level rise. Though not the ice sheet part is still, that's still a little bit hard to predict. They've done well when it comes to the pattern of warming. The fact that the land is warming more than the oceans and the Arctic is warming more than anywhere else. They've done well when it's come to predictions of the statistics of extreme weather. The fact that heat waves are becoming more intense and longer lasting. The fact that rainfall is becoming more intense when it rains. Those are very strong predictions that have come true. People. The predictions of sea ice. Earlier on, we underestimated that, and then people spent time, thinking about the processes, making meta modules, including more processes there. And now the predictions and the hindcasts of sea ice are spot on. The ocean heat content change, right? So there was I mentioned that earlier on, but there was a real discussion in the 1990s where people said, look, if the ocean heat content is not increasing, that means that climate sensitivity is very small and we don't need to worry. And then there was the other folks saying, no, we think climate sensitivity is large, which means that there's an energy imbalance, which means that energy has to end up somewhere. It's going to end up in the ocean. So we predict that the ocean heat content is going to rise at about this rate. Okay.
This is another thing. This is another thing, right, that people don't see in science is the idea that if these models were all wrong, that there wouldn't be someone in the corner going, I'm going to go get my Nobel Prize by showing that all these models are wrong. It just...
Well, but it's the opposite. The Nobel Prizes were given for people showing that the models are wrong.
Exactly. But the idea that there's not that dissent in the room, that somebody would, if we knew that this was complete nonsense, that nobody would jump up and go grab their Nobel Prize, is just not something that happens for anyone who works in science. Knows that there would be someone who took on that task.
Right. But all of these things, it's not a question of people who agree versus people who dissent. It's people who are trying to work out what's going on. Exactly. And at any one time, there's like 100 different ideas. Right. And then we basically go through them and we say, okay, no. Okay, this one's left. Okay, well, what does this one predict? Oh, okay, well, verification. Oh, validation. Okay, could it be more complicated? Yes. Well, then it kind of branches off again and you have, more kind of sub ideas and people keep iterating on that. Now, when it comes to what do you need to know in the public about what's changing, do you need to follow, all of these little sub ideas and subsects and, and slightly different schools of thought? Mostly no. The things that people need to know, which is the basis of, the Framework Convention on Climate Change, which is the basis of the Paris Agreements, which everybody has signed up to, right? What people need to know is that we are increasing the amount of greenhouse gases in the atmosphere. That is causing the planet to warm. It's warming in the way that we anticipated, and the consequences of that warming are being seen now, not just in esoteric measures like the global mean temperature surface anomaly, but in weather systems and in rainfall amounts and in heat waves and in melting glaciers.
Real things that impact real people.
Real things that are impacting real people. And you don't need to be, an Inuit living in the Arctic to be impacted by climate change. Just ask anybody on the west coast of the US last summer. Ask people living in Europe in 2003, or being subject to the floods in 2020, or being subject to the floods in China in 2021. Right? All of these things, we can look at these individual events and we can now see a fingerprint of human activity, right? These things are becoming not every single thing, but heat waves are becoming more intense and more frequent. Intense rainfall, more intense, more frequently, right? These things have a fingerprint of our activities embedded within them. And so that has implications going forward. And so people need to know about that. They need to know about what the minimum amount of change is so that they can prepare, right? So that's the adaptation part. And then the people who are able to make decisions about mitigation, reducing our greenhouse gases, they need to know that those are the things that are causing the climate to change. And they, for the most part, they do know that.
Yeah. Just before we move on to the final question, one thing that Peterson brought up in that Joe Rogan interview was that he said that the errors of these climate models compound like interest. I think that's a direct quote, and essentially sort of flirting with the idea that they kind of become useless as we go out to 20, 30, 40, 50 years. What would you say to that, and what would you say to people who say, well, you can't model out so far, so I don't really know what's going to happen, so let's just go on as we are and not worry about these models.
I mean, so it's wrong. That's not actually how things are. So the error associated, we mentioned three kinds of errors, right? The error associated with internal variability, right? The chaos of the system saturates. It doesn't get massively large. The climate isn't suddenly going to jump into an ice age between now and 2100. I guarantee it. It's not going to suddenly become the Cretaceous by 2100, right? And so if you say, okay, well, the system is like, well, it's just like, Brownian motion, and it goes from infinity to infinity. That's not how the climate works. And the climate doesn't work like that because of things like conservation of energy that doesn't allow the system to really move very far away from where the boundary conditions.
Earth's got a lot of inertia, I guess, and
there is a lot of inertia. So I kind of know maybe what he was reading to get that, but it's totally wrong. The errors of models do not expand exponentially. And so we do have skill. We do have skill 30 years out. We do have skill 50 years out. The big uncertainty 50 years out is our activity, not the models, our activity.
Yeah. If we were being kind to him, we could say that maybe we don't know what humans are going to do, and that's what he was talking about. Some people have tried to sort of sell it in that way, but I don't think that's what he meant. And some of the things, like you say, that he's been reading and posting about suggest that that's not what he meant. But if we were being kind, there are these unknowns of how humans will behave. So the final question I've got for you, Gavin, and it probably is the most important in terms of how we're going to go going forward, is how should we treat these models when we're talking about worldwide policy debates? How should they be incorporated? Because you see a lot of people on one side saying, oh, they're not perfect, so let's just go on as normal. Like we said, the more skeptical. You see the alarmists who are like, God, look at the worst case scenarios, throw everything at it. We need to stop doing anything else and just focus on this issue. How should we be using these models in policy debates going forwards, and how much stock should we put in them, in your opinion?
So we use them in different ways. We've used them historically to raise the alarm about this phenomena, right? And so to that extent, they've done their job. We use them now to help inform local planning decisions, right? So how much coastal flooding can we expect in this location? It turns out that's a slightly more complicated issue than some others, but we're using models in cooperation with all sorts of other things to give people real information about that kind of stuff. So there are policies, that people are using, that the people are working on, that implicitly include quite detailed information from these models and others like them.
And I think there was a really beautiful way that you put it in. I think it was in one of your TED Talks, that the model doesn't need to be perfect to be skillful, right? There's no need to have every single tiny thing dialed in to know that right. there's a higher likelihood that something's going to happen. In fact, this is how we live our lives on a daily basis, right? We never have absolute certainty, but we look at the probabilities, we make decisions based upon them. That's how we live our lives as human beings.
Right. I mean, so the models are not perfect, right? I mean, like, nobody has ever claimed that they are perfect. Nobody's ever claimed that they are inerrant or anything. That would be weird. Yeah. But they are more skillful than not using them, right? Yeah. So if I mean, and we can look through history, all the people that predicted climate without using models were just wrong, right? They just made very bad assumptions that weren't based on quantitative physics, and they made errors. They predict, and there's still a whole bunch of people who are predicting, imminent global cooling because of some extrapolation that they've seen of solar activity, and that's wrong too. And so the models are not perfect, but they are better than nothing. And they have demonstrated that they are better than nothing over 40 years. And so when we look at them now, they are better than nothing. And so we can incorporate the insights that we get from those models into our planning. And people are, the models make a pretty robust case that future warming is really just a function of future emissions, right? Which is interesting. Because that means that we still control how much it's going to warm in the future, right? And
that's quite an empowering message, actually, isn't it?
I think so. Exactly. Yes. And so that's an interesting and relatively robust result from these models. The other robust results are the ones that we've mentioned that we do need to plan for. It's not like we're making large scale decisions based on individual grid points in one single model that was run once, right? I mean, there's no way that somebody's writing a policy to promote cap and trade or some carbon pricing system is paying any attention to the details of what was in the models, right? They're looking at what comes out of the models as a whole, and they're saying, okay, well, those are things that we estimate are going to be bad. We should hedge against that in some effective way. And I think that's how they're used. They're not used because
somebody loves Greta Thunberg, so they're just going to go pick the worst model and do whatever they want. It doesn't work.
No. I mean, that's not how these models work. We can do better, I think, in having these models be tied to policies, right? So, if you've got a policy that says, oh, we're gonna move everything to rail, high-speed rail everywhere, reduce the amount of short-haul airline flights, what impact would that have on climate? I think that's a great question. And so we can test those things now. We tested, what was the impact of COVID and all the restrictions associated on COVID on the climate system, right? And we've done those runs, right? And you can see these very clear effects, mainly associated with cleaner air pollution, cleaner air, less air pollution, because of the reduction in transportation, in car travel. And so you can see those things from the satellites as well. Right, so we can use these models in many different levels, but the big level, the big kind of elephant in the room here is something that we've known for 40 years, which is if you increase the amount of greenhouse gases in the atmosphere, the climate will warm, and that will have bad consequences, right? And so we've known that for 40 years. You don't need more climate modeling to tell you that that's correct, right? We predicted it, it happened, it's going to continue to happen. And all these other people who say, oh, no, all these, none of that is of any relevance. And so, so that's the big issue. I mean, are there, subtleties associated with, well, what if we reduce methane as opposed to carbon dioxide. Yeah, well, you should reduce methane because of its impact on smog and atmospheric ozone and climate warming. Reducing, reduce air pollution as well, right? I mean, we can drill down into the consequences of specific policies on specific gases, and there's a constituency in the policymaking arena where people really care about those kinds of things, but they're not the big picture, right? And so we end up in a situation, and perhaps this is a good note to end on. We're scientists, and so we're supposed to derive great pleasure from wrestling information from the universe, encapsulating it into our theories, making predictions, and seeing them come true. Right, and that's supposed to be our what keeps us going in the morning, right? But that changes when the predictions you're making are things you don't actually want to have be true. Right? So you predict what's going to happen to temperatures, and you go, well, according to our understanding of physics, this is what's going to happen, and then it happens. You don't feel good, right? Because you're still a human being, you're still a citizen. And while your kind of intellectual hat says, yes, look how marvelous it is that we've understood all these things and we've built these massive models.
You don't want it to be, you don't want it to be true.
Actually want it to be true.
Yeah.
Right. And so, Sherwood Rowland, was one of the first people to really encapsulate this. And he was one of the people that did who won the Nobel Prize for the chemistry of ozone depletion way back in the 1970s. And he won the Nobel Prize in the 1980s. He said, what is the point of having done our science and made our models so capable that we can make predictions if all we're going to do is sit around and wait for them to come true? And it really encapsulates our dilemma as climate scientists, which is that we don't want these things to come true, but we fear that they are. And so when people tell us, well, your models can be wrong, we're saying, yes, well, we hope that they are.
and none of that stops us from, when we've done the good science, none of that stops us from having sensible political conversations about how best to do mitigation to keep things, freedom and, the economy going as well as we can. We can still have these sensible debates while not trying to undercut the science that these models are based on.
Have you ever been on the internet?
Well, quite. I think that's a good place to end it. Gavin, I really enjoyed that, and I've learned an awful lot. It's given me an awful lot to think about as well, and I'm sure everyone else will have enjoyed it too. Just as we finish, is there anywhere where I can send people to learn more about what you're doing, what you're saying? Because you've got a hell of a lot of good stuff that's out there. Is there anywhere where you want to send people? And I'll put all the links down in the description.
Sure. I mean, I did like a 12-minute TED talk on this stuff, which had lots of nice graphics and things. You can check that out. My Twitter feed, Climate of Gavin. We cover a lot of this stuff on a pretty regular basis. I have a blog, realclimate.org, where for almost 20 years now we've been discussing some of the ins and outs of exactly these questions. So there's a lot of good stuff there too.
Awesome. I will put all those links down in the description. The TED Talk is particularly excellent and a nice primer for people on a lot of these issues. So, Gavin, thank you so much for taking the time this morning. I really, really appreciate it. I know you're very busy, and hopefully the next time some big issue comes up on this, we can get you back and we can have another chat.
I'd look forward to it.
Thank you very much. Have a good weekend, and let's stay in touch and let's talk again soon.
Thanks. Bye.
Thanks, buddy. Bye now. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.